We will now talk about gravitational lensing, which is a very powerful technique to find about distribution of mass in the universe, whether it's visible or not. As you will recall from the general relativity, it predicts that the presence of the mass, again, whether you can see it in visible light or not, will distort the paths of the light rays passing by. Therefore, we have a method of learning about mass distribution regardless of whether we can see it on any wavelength. This was originally considered by Charlson and Einstein and also Zwicky, but it took until 1979 to find the first real example. This was measurement of a quasar, which turned out to have two images, which are just mirages. They're both the same quasar. And after that, hundreds, if not thousands, of lenses have been found. So the geometry is shown here. If we had a perfect alignment of the observer, the background source, and the lens, and distribution was symmetric, then each azimuth will be equal, and so the image of the background object will be now distorted into a ring called the Einstein ring. If we deviate from that symmetry, either by moving the lens a little bit in the lens plane or by changing the mass distribution to be asymmetric, the ring will break up and we'll see multiple images of a lens source. And this is indeed what's seen in case of multiply imaged gravitational lens quasars. So Zwicky already in 1937 predicted that gravitational lensing should not only be detected, but it can be used to probe mass distribution in galaxies in the universe, as well as to use clusters or galaxies as telescopes to magnify even more distant ones. And after all, it can also be used to test theory of gravity. All of those predictions have come true. As far as measuring masses using gravitational lensing, that took until 1990s and Hubble Space Telescope in order to be able to really do this well. These are Hubble Space Telescope images of a particular cluster that serves as a gravitational lens. All of these blue arches, arcs, and arclets are images of background galaxies that have been lensed by this cluster, split and distorted, and thus the cluster itself is essentially a gigantic lens in space that magnifies and distorts their images. From the distribution and shapes of these arcs and arclets, one can reconstruct the mass distribution in the cluster regardless of where the galaxies are. So the gravitational bending of light in general relativity is twice what you'd infer from Newtonian gravity. Most importantly, it is achromatic. Photons on any wavelength are deflected in exactly the same way. And this is unlike, say, lenses made out of glass. This adds to the power of the method because it's been used not just in visible light, but in radio and also X-rays. Obviously, the effect will be the strongest for the strongest gravitational field. And the strongest you can get is if you compress the lens mass into a black hole. Then you get maximum effect right at its Schwarzschild radius. But in reality, that doesn't happen. Most of the astrophysical objects like galaxies or clusters are vastly larger than their Schwarzschild radii, so the effect isn't quite as strong. Here is a simple schematic geometry shown. It's fairly obvious that there is observer, the lens, and the source in the background, and distortion of the light path.